Okay, let's look at problem 15.98. Here you have a particle in space at A, which is at the coordinate position -4, 5 in the y direction, and 6 in the z direction. And it's pointing at B, which is 8 in the x direction and 9 in the y direction. So what we want to do here is we want to find the angular momentum about O. So this particle A has a weight associated with it, and that weight is 10 pounds. So our HO equals mass times our velocity. Well, R cross mass times our velocity, actually. R cross mass times velocity. Mass is a scalar. So we need to figure out what these vectors are. Let's do mass times velocity, or just velocity. We can multiply it by mass later. So velocity is going to equal the magnitude of our velocity, which is given here as v equals 14 feet per second. Not 19, but 14. So to find the vector in this direction, what we need to do is we need to take the magnitude of 14 and multiply it by a unit vector in that direction, which we can obtain by looking at a vector, position vector in that direction, which is 12i plus 4j minus 6k. 12 because that's essentially 8 plus 4, the distance from there to there, and 4 because we have essentially 9 minus 5 to get 4, and 6, we're just going down 6 in the z direction. Let's move those to the top because we still have to divide this by the magnitude of that vector to get a unit vector. So we square each of those coefficients and take the square root. So the square root of the denominator actually equals 14, so you end up with just this vector again. Now, R equals, well, we can draw a position vector anywhere we want to this line, and perhaps the easiest way to do that is to draw our position vector in this direction. So it's only in the xy plane that way. It contacts the line of action of this force, and that's good enough to calculate for our moment. So R is then 8i plus 9j plus 0k. And that's why we did that, so we could have a zero term. So the moment of our momentum about O is just mv, or R cross mv, as we stated up here. So we can set up our matrix then. I, j, and k. So for R, our coefficients are 8, 9, and 0. And this is important that this is a 0. And then for mv, we've got to make sure we put our mass in here. This is easy to forget about the mass, but let's not. Remember, we have to divide our weight by 32. 32.2 would be more accurate, but just did it by 32. and this is minus 6. Okay, so again, you can calculate this determinant by any method you like. I think that the easiest way to do this is just by hand with the cofactor method. Remember, there is a sign convention that is used when we are coming up with the cofactor. So in this case, I'm going to use, if you recall from your mathematics, I'm going to use this line here because there's a 0 in there, and it makes this really easy and quick to do. We create a cofactor here with the actual factor of 8, but this is in the negative position, so we got to put a negative on there. Then we look at the minor matrix associated with that. So our minor matrix then is this times that minus this times that. So that's 60 minus 60 over 32. This is a negative, subtracted by 40 over 32 multiplied by k, unit vector k. So that's in that. Next, we'll take the cofactor of, based on this 9, which is positive because of position here, positive, and our minor matrix are these outside terms. Again, we have minus 60 over 32 times I this time, and then we're going to subtract off 120 over 32k. We quickly just group terms. So for I, we have this term, and that results in a minus value, minus 16.88i. For j, we have just this term, 8 times this, so it's 480, so it's positive, divided by 32, which is 15j. And then for k, we have two terms. We have, of course, this term and this term we have to take into account. So we take minus 8 times this, and positive 9 times this, which is negative, and we end up with a minus 23.75k. And that, in fact, is our H naught. Very quick way to do determinants using cofactor method. In fact, it's almost ridiculously trivially easy if you have 2 0 values in your matrix, because you can pick any line or column to work as your cofactors. So let's look at the fundamental problem 1524. Now we have a couple moment on these two weights, so this thing is going to rotate counterclockwise, and we also have an applied moment here just to actually speed this thing up, and moment about O, and that moment equals, I won't put moment about O because we'll want to use that, but that moment equals 8t. So it's just a linear value, but it's a function of time, Newton meters. This whole thing exists in the horizontal plane, so we don't have to worry about weights. And in this problem, we want to find v after 4 seconds. So let's use our impulse, linear impulse, or angular impulse momentum relationship. So h naught 1 plus the integral of some of our moments dt equals our angular momentum, final angular momentum. So we're going to start from rest here, which means this term goes to 0. So that leaves us with this for our sum of moments. 8t is an applied moment about O, and we're taking moments about O. And the way to calculate this couple moment is the distance between the two forces times the force, so 10 times 1. Let's take that from 0 to 4 seconds, which is part of the problem statement. And then this equals our final angular momentum. So each of those balls will have a velocity perpendicular to the bar. So let's just say velocity, then multiply that by the mass, 10 kilograms, and then our perpendicular distance of 0.5. That's one mass, and then the other mass is spinning in the same direction. We will have V times 10 kilograms times 0.5. So it's essentially 2 times. So this is essentially 2 times this, or 10 times V. And this is our final velocity. We may as well call that 2. So this then equals 8 times 4 squared over 2 plus 40 equals that. And so our final velocity is 10.4 meters per second.